Welcome back for chapter 8.3. We are going to be talking about confidence intervals, but with proportions. So confidence intervals for proportions, which means we're dealing with qualitative data. Okay, so proportions, we see them as fractions. So as X is a number of successes and N is a sample size, that's how we're seeing proportions. And we can see them as fractions. Remember, they come as fractions. They come as in decimal form, and they also come in percent form. So that's what we're kind of looking out for. We're going to have an error bound, but it's going to be the EBP because it's the error bound for the proportion. And that is going to consist of a critical Z. So we're at a critical Z like we were in 8.1. And our standard error right here is the square root of the P hat times the Q hat over N. So P hat and Q hat, remember, are from the sample proportion. We're trying to estimate the true proportion P. And remember that Q is the complement of P. So they add to make 1. And we're going to go back to finding the normal critical Z. So let's just jump into an example. You can follow it through. Also remember that everything that I do in Desmos can be found in Canvas in the Desmos link. So it says let X equal the number of people in the sample who have cell phones. X is binomial. So X is binomial, where it's either you have a cell phone or you don't. It's 500 is N in our sample. And the proportion that had cell phones is 421 out of 500. Okay, so suppose that a market research firm is hired to estimate the percent of adults living in a large city who have cell phones. 500 randomly selected adult residents in the city are surveyed to determine whether they have cell phones. Of the 500 people surveyed, 421 responded yes, they own a cell phone. Using a 95% confidence level, compute a confidence interval estimate for the true proportion of adult residents of the city who have cell phones. So first thing we're going to do is calculate our P hat, which is X divided by N, and that comes out to be 0.842. That is our sample proportion. We also call that our point estimate. Q hat is 1 minus P hat, so that's 0.158. Then we go to our confidence level is 0.95, so our alpha is 0.05, and our alpha divided by 2 is 0.025. So if we use Desmos or graphing calculator or our handy dandy sheet here at 0.025, we can see that that Z is 1.96, and that's what we're going to use. So the error bound for a proportion is our critical Z, 1.96, times the square root of P hat times Q hat over N. And you can do all of that in a graphing calculator or on Desmos, and you get 0.032. So to find our confidence interval, we're going to take our P hat minus our EBP. So there's our lower bound. And then P hat plus our EBP, which is our upper bound. So our confidence interval is 0.810 to 0.874. And our interpretation is we estimate with 95% confidence that between 81% and 87.4% of all adult residents of this city have cell phones. And remember, when we do our interpretation, I will be turning my decimal form of my confidence interval into a percentage, because when we describe something to our readers, we usually use percentages to do that. So let's go to example 2. I'm going to put this together on our own. Suppose 250 randomly selected people are surveyed to determine if they own a tablet. Of the 250 surveyed, 98 reported owning a tablet. Define the variables X and P hat. So X is the number who own a tablet, and P hat is the proportion of the sample who own a tablet. Now we know that this is a yes or no question, it's binomial, but we're going to use the normal distribution to actually get our confidence interval. Okay. Calculate p hat. And so p hat is x divided by n, and x is 98 divided by 250. And 100 divided by 250 is 0.392. Using a 95% confidence level, compute a confidence interval estimate for the true proportion of people who own tablets. And we're going to sketch that. So remember, confidence intervals always have a negative and a positive critical value because it's always two-sided. And so we said that 0.95 is here. So that means that critical level is 0.95. So alpha is 0.05. And alpha divided by 2 is 0.025. So z of 0.025, we just did this on the last problem, is 1.96. So we've got 0.025 here and 0.025 there. And we always want to make sure that those add to make 1. So 0.025 plus 0.95 plus 0.025. I'm just validating that those equal 1. Okay. So the error bound of the proportion is going to be, just remind ourselves with symbols, the critical z times the square root of p hat times q hat divided by n. And we're going to do all this in Desmos, kind of by hand in Desmos, but then there's also one of those formulas that we can use, like we use in 8.2, and I'm going to show you that as well. So 1.96, the square root of 0.392, that's from up here. And then remember that q hat is 1 minus p hat, so 1 minus 0.392 is 0.608. So times 0.608 over n, which was 250. So let's go to, so that we can see all of this worked out. Click on that. So the p hat is verified 0.392. And then there is a verification using the inverse CDF right here. We can see our critical z value. And then our error bound margin is right here. So that's 0.0605. And then we took our p hat and subtracted our error bound margin and added it. And there is our confidence level. So our lower bound is 0.33. I always go to so 0.331, 3 decimals in the decimal form, and then we'll translate that to percentage in our interpretation. And then 0.453, okay, is our upper. And I'm going to show you this using the other, this is our, it's going to be, the title will be CI proportions for one sample. So you're going to enter your sample size of 250. We're going to enter our proportion that we came up with, which was 0.392. Oops, I have too many decimals. Okay. We don't need an H though, because we're going to use this HO in chapter 9 for hypothesis testing. But we do need to put in our alpha. So our alpha we said was 0.05. And then we're going to click right here where my arrow is. I'm going to turn on the graph just so you can see. I'm going to click on my confidence interval and I'm going to go down and see that, yep, our confidence level is 0.95 and there's our lower and there's our upper. And it just validates what we already have. So you can go straight to this. Once you've got your formula filled in, you can go straight to this little program and use this for your confidence level, for your interval. So let's go to our paper and verify that we all have the same thing. So there's my error bound for proportion. There's my confidence interval. And interpret here. So we are 95% confident that the true proportion of people, they didn't say if it was the United States or a particular city, but of people that own a tablet is between, and remember, I'm turning my lower and upper into percentages. So 33.1% and 45.3%. That was example 2. Let's look at example 3. Get some good practice here. For a class project, a political science student at a large university wants to estimate the percent of students who are registered voters. He surveys 500 students and finds that 300 are registered voters. Describe X and P hat in words. Don't have a lot of space, I'm gonna use a pen. So X is number of registered voters. And P hat is proportion of sample that are registered voters. Which distribution? We're going to use the normal distribution. Calculate your P hat. So P hat is X divided by N. I'm reminding myself of my formula every time. And X is 300 out of the 500. So we're going to go through and find out that in Desmond's place. Just write down what we can. So we have minus C. I'll do this for with marker. Minus C and plus Z. So if the confidence level is 0.9, alpha is 1 minus 0.9 or 0.10. And alpha divided by 2 is 0.05. Make sure you use a calculator to go 0.10 because it's easy to get your kind of decimals mixed up here on the alpha divided by 2. So 1 minus 0.9 and then divided by 2 is 0.05. Okay. And so Z of 0.05. This is 0.9, this is 0.05, and that is 0.05. Down here, we're making it is 0.05. That Z is 1.645. 1.645. And 300 divided by 500, our P hat is 0.6. Okay, that means our Q hat is equal to 1 minus P hat. So 1 minus 0.6 is 0.4. Okay, so our error bound here, our ABP is 1.645 times the square root of 0.6 times 0.4 divided by N, which is 500. And then we're going to get our interval here, and then we'll do our interpretation. So let's go ahead and go to Desmos so that we can check this out. Okay. So we have everything for our theorem bound of the proportion here, and then here's our lower bound and our upper. So our lower interval is 0.564, and our upper is 0.636. Okay, and we can just practice with our little computer program from Desmos. So let's go up here and put in our n was 500. The proportion we came up with for p hat is 0.6. And then the only other thing we need is alpha, and this time alpha is 0.10. Then we can go straight down to our lower and upper, and that validates the lower and upper that we had gotten here. So here's our lower, and here's our upper. Okay, so let's interpret this. We are 90% confident that the true proportion of students who are registered to vote is between 56.4% and 63.6%. That was okay. Let's look at example 4. We've got 4, 5, and then we've got some sample size that we're going to work on. So example 4 says a student polls his school to see if students in the school district are for or against the new legislation regarding school uniforms. She surveys 600 students and finds that 480 are against the new legislation. So define the variables. So X is number of sample who are against whatever that legislation is. And P hat is proportion of sample against. Which distribution should you use? We're going to use the normal because it's a binomial, and we're going to use the normal because it best estimates for the confidence interval. The binomial follows the normal curve. Okay, calculate P hat. So P hat is 480 divided by 600. So that comes up to 0.8. So Q hat is 1 minus 0.8 or 0.2. Compute a 90% confidence interval. Okay. So we are going to draw our curve here. So this is going to be, this is just like the one the last time because it's 0.9, 90%. So when the confidence level is 0.9, alpha is 0.10, and alpha divided by 2 is 0.05. And we said z of 0.05 was 1.645. So 1.645 times the square root of 0.8 times 0.2 over 600. So let's go to Desmos. Let's just go right to this program here, and let's just do this one first this time. So we have 600 in our sample. The proportion is 0.8, and our alpha is still 0.10. So here's our lower bound, 0.773. And our upper bound is 0.827. Okay, so before we go to how we worked it out in the other Desmos tab, I want to remind ourselves that we can find our error bound margin from our interval. So our error bound margin will be our upper minus the lower divided by 2. So 0.827 minus 0.773 divided by 2. So let's do that. 0.827 minus 0.773 divided by 2 is 0.027. So this should be 0.027. So let's go and validate that in Desmos. This is good practice for us to kind of work in different directions. And there is our error bound margin, 0.027 rounded. Excellent. Okay, let's try one more together. The next one is it's over fruit snacks. So it says, in 6 packages of the Flintstones real fruit snacks, there were 5 Bam Bam snack pieces. The total number of snack pieces in the 6 bags was 68. We wish to calculate a 96% confidence interval for the population proportion of Bam Bam snack pieces. Define X P hat. Okay, so X is the number of Bam Bam because we want a specific shape. And P hat is proportion of Bam Bam. And these are from the sample. We're using the sample to predict the population. So we're going to use a normal because we actually have a binomial distribution. It's yes or no, and the normal curve displays that. So calculate P hat, which is 5 Bam Bam out of the 68, which is 0.0735. 0.0735. So Q hat is 1, minus that answer. So 0.9265. Construct a 96% confidence interval for the population proportion of Bam Bam snack pieces per bag. So we are, so now the critical level is 0.96. So 12.5 is 1 minus 0.96, 0.04. So alpha divided by 2 is 0.02. And so we need to know z of 0.02. So the negative z, positive z, this is 0.02, 0.02, and 0.96. Okay. So 0.02 is on our curve on our paper, which this paper is just handy. If you've got this handy, you don't have to go to your calculator every time. Is 2.054. Okay. So 2.054 times the square root of 0.0735 times 9265 divided by n, which is 68. So there's our proportion, and that's validating our critical Z 2.054, and this our error bound proportion is 0.0650 when we round it. And then our lower, when we calculate our lower bound of the interval is 0.0085, and then our upper is 0.1385. Okay. So let's go back to our paper. It's our prediction, lower and upper. It says, do you think that 6 packages of fruit snacks yield enough to give accurate results? Why or why not? I don't know. That's a good question. I would think it's not. But remember, we can go to our central limit theorem. And look at NPQ, and it's supposed to be bigger than 10. So that would be 6 times P is 0.0735 and Q is 0.9265. And let's see what that actually comes out to be. That is not big enough. It's 0.409. It's less than 10. So I would say it's not enough. And so we have to figure out what isn't enough sample size. And so we're going to look at sample size for proportions. We already did a little bit of sample size for means, but we're going to look at sample size for proportions now. And remember that these formulas are all in your formula packet that you will be able to use on the final exam. So there are the formulas for the confidence intervals that we've been working with. Here are the sample size formulas that we are going to work with. And we're going to go from there. So calculating sample size. If researchers desire specific margin of error, then they can use the error bound formula to calculate the required sample size. The error bound formula for a population proportion is as follows. So if you have a prior estimate for P, let's say you did a sample and confidence interval last summer on the people that were happy with the weather. Then you can use this formula here for sample size because you have a prior estimate for P. You kind of have an idea of what they said last summer. If you don't have a prior estimate, you must use this one here. Now, just like in lesson 8.2 in 8.1, we must always be rounding up. That's the important part. Okay, rounding up to a whole integer, to the next integer. Suppose a mobile phone company wants to determine the current percentage of customers aged 50 plus who use text messaging on their cell phones. How many customers aged 50 plus should the company survey in order to be 90% confident that the estimated sample proportion is within 3 percentage points of the true population proportion of customers aged 50 plus who use text messaging on their cell phones? So we know our error bound of the proportion is 0.03 because they said they wanted to be within 3 percentage points right here. And our critical Z is always going to be the alpha divided by 2, which is 0.05, because the confidence level is 0.9. Alpha is 1 minus 0.9 of 0.10. So alpha divided by 2 is 0.05. So we're using Z of 1.645 here. However, in order to find N, we need to know the estimated sample proportion. Remember that Q hat equals 1 minus P hat. But we do not know P hat yet. Since we multiply P hat and Q hat together, we make them both equal to 0.5, because that would be the highest possible. Okay, the largest possible product gives us the largest N. So this gives us a large enough sample so that we can be 90% confident that we are within 3 percentage points. Formula is here. So N equals Z squared times P hat times Q hat over EVP squared. So we have 1.645 squared times 0.5 times 0.5. This is the 0.25 that we see in this formula here when we don't have a prior estimate. That's where they get that. And so they divide by 0.03 squared and we get 751.7, but we round up to 752 because it has to be an integer. So the sample size should be 752 cell phone customers age 50 plus in order to be 90% confident that the estimated sample proportion is within 3 percentage points of the true population proportion of all customers age 50 plus who use text messaging on their cell phones. So let's look at it. Suppose an internet marketing company wants to determine the current percentage of customers who click on ads on their smartphones. How many customers should the company survey in order to be 90% confident that the estimated proportion is within 5 percentage points of the true population proportion of customers who click on ads? So N is going to be 9. We're using 90%, which is what they used up here. So we can use the same critical Z. So that's going to be, we're using this formula here because we don't have a prior estimate. So it's 0.25. And then our critical Z of 1.645 over our error bound of the proportion, which is 0.05 squared, because they want to be within 5 percentage points. 5 parentheses 1.645 parentheses, and then we're going to square that. Sorry about that. So here's what we get, 270.6. So that means we have to round up. So N should be 271 customers. And that is the end of chapter 8. Please reach out if you have any questions at all or need help on the homework assignments. And also a reminder that there are a couple of projects in this chapter. Please make sure you're working on those. And have a blessed day.